Okay, next up, integral trigonometric functions. Okay, so same thing I'm going to say is what I've just said maybe for the exponential functions as well. So for trigonometric functions, the best thing you could keep in the back of your head is what would I do if I was differentiating this? Because most of the time, I'm saying most of the time, it's all of the time, what you're going to do is nearly the same, but also opposite, which is complete contradiction. I suppose what I mean by that, of course, is for example, with our trig functions, if we had a function such as sine 3x, if I was differentiating that function, well, sine goes to cos, so I would differentiate the function part to get cos 3x, and I would also differentiate the angle part, which would give me 3. So I would get 3 cos 3x, and I would multiply by that 3. If I'm integrating, I'm going to follow a lot of the same steps. So I would integrate the function itself, sine, which now are, so let's say we want to go backwards. So we start with cos 3x. I would integrate the function itself, cos. Cos is going to go to sine, because think about your derivatives there. Sine differentiates to cos, so cos must have come from sine. So sine 3x, but now I'll divide by 3. So still the derivative of the angle part, but as opposed to multiplying, we will divide by it. Okay, so I suppose that's the thing to watch out for here, because really, like looking at kind of the formula you're presented with, like this is kind of mainly what you're going to have, and you need to watch out for types such as the second two rows here, where we have maybe a number in front of the angle. Bearing in mind, sine integrates to minus cos because we know cos differentiates to minus sine, so that idea of that kind of connection between the two, and then cos integrates to sine. As I've said, sine differentiated to cos kind of straightforwardly, so that integral obviously is straightforward as well. So those two I suppose are there for you to not forget. And then in terms of the angle part, just remember, still differentiate the angle or still take the number in front of the angle, but divide as opposed to multiplying by it. So we'll look at some of these examples here, two definite integrals, so I'm given particular values to use for angles here as well. Cos 5x minus sine 2x. Okay, so cos of 5x, well, cos integrates to sine, so sine 5x, and we divide by 5, which is the derivative of the angle part here. Sine, so sine integrates to cos, sine integrates to minus cos, and again we divide by 2, which is the derivative of the angle part here, and I need to evaluate this at 0 and pi. So let's just simplify everything here first of all. So sine 5x over 5 plus cos 2x over 2, evaluated at 0 and pi. So sine of 5 pi over 5 plus cos of 2 pi over 2. And remember what we said as well previously, or think about kind of what we know about trig functions. We can't just disregard a value of 0 in a trig function here, because when it's inserted or when the function's evaluated at 0, there could well be a value here, and particularly looking at cos, for example, in that respect here. So sine of 5 pi, well, let's try it out. Sine of 5 pi is 0, so 0 over 5 plus cos of 2 pi, sorry, the wrong one, cos of 2 pi, let's go again, is 1. So 0 plus a half minus, let's try sine of 0, is also 0. So sine not contributing an awful lot here, cos of 0 is 1, plus a half, and we actually just end up with an overall answer of 0 here, is what it is. We look at the next one. So sine x cos x dx. Okay, so again, looking at this function now, if I was looking at this, this is a product of two functions here. So it's a sine function times a cos function. Now, again, I've been saying it, I suppose, throughout a few of these videos, but we don't have a formula that we need to know that allows us to compute products of integrals. Okay, obviously there are formula and there are ways of doing it, there are methods of doing it, but not that we need to know for this course. So in order to do this, we need to look elsewhere. So we look at the expression we're given, sine x cos x, and for me looking at that, that is ringing bells of trigonometry to me, and of identities, and of things that I've seen before. Maybe not exactly the correct format, but it's definitely reminiscent of something there. And what we're going to need here is a trig identity. Okay, and one of our trig identities is that sine 2a is 2 sine a cos a. So sine 2a is 2 sine a cos a. So what that means for me is that this function that I'm trying to differentiate here could be written as a half sine 2a, or sine 2x, I suppose, to keep it the same. So the idea here is sine 2a would be 2 sine a cos a. We just have sine x cos x, so this is a half sine 2x. Now, we can also always factor out a constant when we're doing our integrals. So it's not that I need to now rewrite this as sine 2x over 2. I can actually factor out the half here just to allow me to do my integral a little bit easier. So computing my integral here is going to give me, let me see, sine goes to minus cos 2x over 2. Okay, and dividing by 2 there, because that is the derivative of the angle part. Okay, so sine goes to minus cos, so keep the function, so minus cos 2x, keep the angle the same there, and then we look at the angle itself. So 2 parts to consider in nearly separate there. Okay, so continuing onwards, I know this needs to be evaluated at pi over 2 and 2 pi. Okay, so I suppose I've 2 different ways of considering this. One way, which I might do here, and which we've maybe seen before, would be to bring the 2 on the outside, bring the half on the outside back inside with the function here, and consider it as minus cos 2x over 4. Just makes it maybe a little bit easier for me in computing my integral here. So cos 2 times 2 pi over 4 minus cos 2 times pi over 2 all over 4. Okay, so let's calculate the value of these now. So minus cos 2 times 2 pi over 4 is minus a quarter. And again, my pi over 2 here is a quarter as well. So minus a quarter is minus a half here. Okay, so a good example there of using a trig identity and why that's important for us in some of these questions here. So how we recognize that, I suppose, is recognizing that that is a product, that expression is a product. And I suppose that's something that people maybe struggle with a little bit too, is even just identifying when we can't use these rules. So essentially, any time that if we were differentiating, you would say, oh, I will use the product rule, or oh, I'll use the quotient rule, you aren't able to do that. So you need to be looking out for those cases so that you can look for alternative methods then of doing it. Let's look at an exam question here. Find 5 cos 3x dx. Okay, straightforward enough, I suppose. Let's factor out the 5. Compute the integral. So cos, when we integrate it, goes to sine. So sine 3x, we remember now that we're dividing by 3 because that's the derivative of the angle part. So 5 sine 3x over 3, and I need to remember my plus c here because I have no, it's not a definite integral, I have no bounds on my integral. And of course we could write that in a different way if we wanted. We could write that as 5 over 3 sine 3x plus c if we wanted to just express it slightly differently. Looking at one other example here, sine x plus e to the power of 4x, so tying together trigonometric and exponential, the two maybe slightly different types of integral that we could have. When we're completing an integral like this, it can be maybe helpful for us to consider them as 2 separate functions, and it's a sum of 2 functions. So I know from my rules for integration that a sum of 2 functions can be rewritten as a sum of 2 integrals. Well, sine goes to minus cos x, or I suppose came from minus cos x. E to the power of 4x is e to the power of 4x, and divided by 4, as the derivative of the angle part there. And I must remember my plus c as well. So minus cos x plus e to the power of 4x over 4 plus c. Okay, so key things here in terms of trigonometric functions are going to be, again, familiarity with your rules there, making sure that we're happy with the rules when we have a number or a term or coefficient of our angle term there, and then also what we saw about the need in some cases for trigonometric identities and computing some of these integrals, and how that can be maybe an unexpected but necessary change to make in computing these questions.